Welcome to The Explainer. Every now and then, a piece of research drops that just changes everything. Today, we're unpacking exactly that. It's a 2017 paper from researchers at Google Brain and Google Research, and it's got this deceptively simple title: Attention is All You Need. If you've ever interacted with modern AI and found yourself wondering how on earth did this get so smart, so incredibly fast, well, you're looking at ground zero. We are going to demystify exactly how this single document completely rewired the landscape of machine learning forever, and we'll break it down so the absolute genius inside actually makes sense.
Now, to really grasp the impact here, you kind of have to realize how totally shocking their central claim was to the community. They were talking about, and I quote, dispensing with recurrence and convolutions entirely. No way, right? To a computer scientist back in 2017, that sounded almost absurd. Recurrence and convolutions, they were the absolute bedrock of complex AI models. To suggest just throwing them out completely, it's literally like telling an engineer you've invented a car that dispenses with the engine and the wheels entirely. It was a massive, incredibly bold swing.
So, how did they actually pull it off? Well, here's our roadmap for today's explainer. First, we'll look at the core problem with the older sequence models. Then we'll introduce their radical new architecture, the transformer. Third, we'll decode its secret sauce, self-attention. Fourth, we'll take a peek inside the actual architecture. And finally, we'll look at the record-breaking results.
Part 1, the problem with sequence models. Let's get right into it.
Before we talk about the models themselves, we really need to define what they were actually trying to do. The overarching task here is called sequence transduction. I know, it sounds like heavy jargon, but really it's just the process of translating one sequence of data into another. The absolute easiest way to visualize this is language translation. You feed the AI a sequence of English words, and you want it to output a matching sequence of German words. Super simple in theory, right? But for a machine, incredibly difficult in practice. For years, the absolute gold standard for solving this translation problem was something called a recurrent neural network, or an RNN. And the really crucial thing to remember here is right in the definition, step by step. An RNN processes information linearly. It reads the first word, generates a hidden state, then moves to the second word, updates its state based on that previous word, and so on. It basically reads exactly like you and I do, one word at a time, from left to right. But here's the catch. Reading like a human turns out to be a massive bottleneck for a computer, because an RNN literally has to finish word number 1 before it can even look at word number 2. You can't run those calculations simultaneously. You just can't parallelize the work. And this creates two huge problems. First, it's incredibly slow. And second, it creates terrible memory constraints. Think about it. If the AI is translating a really, really long paragraph, by the time it gets to the very end, it has mathematically started to kind of forget the context of the words from the very beginning. That sequential nature is just a fundamental flaw. Which brings us to section 2, introducing the transformer. Okay, this is where the magic actually happens. Those old recurrent models we just talked about, they've required what's called O of n sequential operations. In simple terms, n is just the length of the sentence. So if a sentence has 100 words, it takes 100 sequential steps to connect the first word to the last word. The transformer, however, requires O of 1 operations. What does that mean? It means no matter how long the sentence is, it takes a constant single operation to connect any two words. It takes this linear, time-consuming slog and turns it into an instant connection. It completely eliminates the need to read step by step, and in doing so, it unlocks massive parallelization. Section 3, understanding self-attention. Self-attention is basically the superpower of the transformer. The technical definition is that it's a mechanism relating different positions of a single sequence to compute a representation. But in layman's terms, instead of reading left to right, self-attention looks at every single word in a sentence all at once, simultaneously. It allows every single word to look at every other word to figure out the overall context. For example, if you have the word bank, self-attention instantly checks the rest of the sentence to see if you're talking about a riverbank or a financial bank. It captures those global dependencies regardless of how far apart the words actually are. It's brilliant. Now, under the hood, self-attention uses a very specific mathematical recipe. It's called scaled dot product attention. But let's just walk through this 3-step process like it's a simple filing system. Step 1, the model creates a query, which is what it's looking for, and checks it against a set of keys, which are basically labels for the info it already has. Step 2, it applies a math function called softmax, and all softmax does is assign a weight, like a percentage of importance, to those matches. Step 3, it outputs the values, which is the actual useful information, but now it's heavily weighted toward the words that matter the absolute most. Oh, and it scales the math down slightly just so the numbers don't get wildly large, hence the scaled part. Basically, it's a rapid-fire sorting mechanism to figure out which words are paying the most attention to which. Moving right along to section 4, inside the architecture. All right, so here is the actual transformer architecture, straight out of the paper. Now, don't let the complex boxes intimidate you. Let's just trace the flow together. Over on the left side, you've got the encoder stack. Your data, like say an English sentence, goes in there. It passes through those self-attention mechanisms and feed-forward networks, processing all the words at once into this dense mathematical representation. Then that representation gets passed over to the right side, the decoder stack. The decoder uses all that info, along with its own masked attention layers, which just ensures it doesn't cheat by looking into the future, to spit out the translated sentence in German. It is such a clean parallel flow. But here's the thing. The transformer doesn't just do this self-attention trick once. It relies on something called multi-head attention. This means it runs that exact same attention process multiple times in parallel, specifically 8 different times, or through 8 different heads. Why do that? Well, because a single word can have a bunch of different relationships in a sentence, right? One head might pay attention to the grammar, another head might focus entirely on the emotion, and maybe another on the literal subject. It lets the model deeply understand nuances from entirely different representation subspaces, all at the exact same time. There is, however, one final puzzle piece here. Think about it. If the transformer processes every single word simultaneously instead of linearly, how does it know what order the words are actually supposed to be in, right? The dog bit the man is very, very different from the man bit the dog. The solution they came up with is positional encoding. Before the data even enters the network, the model injects mathematical timestamps using sine and cosine wave functions. Because the AI reads the whole shebang at once, it absolutely needs these waveforms added directly into the data to remember the absolute and relative sequence order of the original words. It's just a brilliantly elegant solution to the problem of losing that sequential reading order. And finally, section 5, record-breaking results. So the researchers put their money where their mouth is. They tested the transformer on the standard English to German translation task, and this was the result, a 28.4 BLUE score. Now, if you're not familiar, BLUE is simply a metric used to evaluate the quality of machine-translated text. And let me tell you, this number completely shattered existing records. It established a brand new state-of-the-art score, beating the previous best results by more than 2 full points. And incredibly, the single transformer model even beat out ensembles. And ensembles are basically these massive combined teams of previous state-of-the-art models working together. The transformer beat all of them. But it wasn't just about the quality of the translation, it was about the raw efficiency. Training their big transformer model took just 3.5 days, using 8 GPUs. When you compare that to the previous state-of-the-art models from the literature, the transformer achieved way better results at a mere fraction of the training cost and time. By removing that sequential bottleneck, they didn't just build a smarter model. They built an incredibly fast, highly parallelizable model that saved absolutely immense amounts of computing power. A real game changer. The paper wraps up by basically proving its very title: attention is all you need. They literally stripped away the legacy components of AI, leaned entirely into self-attention, and it changed the world. So the really crucial takeaway is this. If self-attention can eliminate the need to read data sequentially for language, what other complex, time-consuming tasks could this parallel architecture unlock next? Images, audio, video? The foundation laid in this 2017 paper is exactly what powers the massive generative AI tools we all use today. It is a true testament to rethinking fundamental bottlenecks. Thank you so much for joining me for this explainer. Keep asking questions and keep exploring the incredible architecture of the technology around you.